Hello, this video is going to be about three things. First, finding the molar mass of a compound. Second, finding the percent composition of a compound. And third, what the difference is between an empirical and a molecular formula. So let's get started with finding the molar mass of a compound. This is a periodic table. I hope you've seen one before. This is what the element boxes look like. They have an atomic number, an element symbol, and a molar mass. The number down at the bottom is called the molar mass of the chemical, and it tells you how heavy 1 mole of that atom would be. So if you had 1 mole of zinc, it would weigh 65.41 grams. The molar mass tells you how much mass 1 mole of an element is in grams. So 1 mole of zinc, 65.41 grams. Finding the molar masses for elements is really easy. You just look it up either on the table or you can Google it. Finding the molar mass for a compound can be more annoying. For example, how much does a mole of zinc nitrate weigh? Well, first, you need to count the number of each element you have. So in this case, I have 3 zincs, and I have 2 nitrogens. Every single zinc weighs 65.41 grams, and every single nitrogen weighs 14.01 grams, or every mole of zinc and nitrogen, I should say. And then you add up all the masses. So in this case, I have 3 copies of zinc, so I'm going to take zinc's mass, multiply it by 3, because if you add these up, you'll get this much mass from the zinc. And then you will also add up all the mass you get from the nitrogen. So I have 2 copies of nitrogen, so I multiply nitrogen's molar mass by 2. And then you add those up. So you add up the contributions of the 3 zincs, this right here represents these 3 zincs, and then the 2 nitrogens. So then you add to that the contribution from the 2 nitrogens, and you get 224.25 in this case. So that is the molar mass of this chemical. You just add up the molar masses of every atom involved. As an example, what's the molar mass of H2O? So H2O has 2 copies of hydrogen and 1 copy of oxygen, so the mass will be 2 times hydrogen's mass plus 1 times oxygen's mass. So you look up hydrogen and oxygen on the table. Hydrogen has a mass of 1.008. Oxygen is 15.999, so you plug those in. 2 times hydrogen's mass, plus 1 plus oxygen's mass, because I have 2 hydrogens and 1 oxygen. Put that into a calculator and you will get 18.015 grams. What's the molar mass of CaCl3, calcium chloride? Well, the process is the same. I have 1 calcium and 3 chlorines. So I take 1 copy of calcium's mass and I add 3 copies of chlorine's mass, because I have 1 calcium and 3 chlorines. So I just have to figure these out by looking them up on the periodic table, or Googling them, I guess. Calcium has a mass of about 40, and chlorine has a mass of about 35, so you plug those in. You put it into a calculator, and you get 146.437 grams. Finally, what's the molar mass of MgOH2, magnesium hydroxide? So you've got to count how many magnesiums, oxygens, and hydrogens you have. I have 1 magnesium, I have 2 times 1 oxygens, and 2 times 2 hydrogens, because remember the 2 goes to everything inside the parentheses. It's a polyatomic ion. So I have 1 copy of magnesium, 2 copies of oxygen, and 2 copies of hydrogen. I can figure out the molar masses by looking at a periodic table. Magnesium's mass is about 24, hydrogen's is about 1, oxygen's is about 16, so you can plug those in. You can round them if you want, but I'm not rounding them. So 1 magnesium, 1 times magnesium's mass, plus 2 times oxygen's mass, plus 2 times hydrogen's mass, and then what you get is 58.319 grams. So that is the molar mass of magnesium hydroxide. If you ever need to use the molar mass of a chemical, just add up the molar masses of all the different parts. So that was part 1. Part 2 builds on this, and it's about percent composition. The percent composition of a molecule tells you how much of a compound's mass is made of each element by percent. So for every element, you find the percent composition by getting the number of atoms of an element times the mass of that element divided by the total mass of the chemical, and then you multiply by 100 to make a percent. I know this is a freaky slide. I'm going to show you how it makes sense, but this is the formula that you would use. So for example, if I wanted to get the percent composition for zinc nitrate, for every element, I would get the number of atoms of zinc times the mass of zinc, divided by the total molar mass, and then I would also do the same thing for nitrogen. This is really what it means. You have all these atoms, and I'm asking what percentage of this mass is made of the zinc. So to figure out the percent, I take the mass of the zinc atoms, just the zinc atoms, divided by the mass of the whole thing, times 100. So in this case, I would take 3 times 65.41, because I have 3 copies of that on the top, divide that by the entire molar mass on the bottom, and then multiply it by 100 to make it a percent. And this would be 87.5% zinc. So 87.5% of the mass is made of zinc. I would do the same thing for nitrogen. So I would take the mass of the whole chemical on the bottom, all of it, and then just take only the nitrogens, put those on the top. So the mass of the 2 nitrogens divided by the whole mass times 100. That's going to be 2 copies of nitrogen divided by the whole molar mass times 100. That'll give me 12.5% nitrogen. So this tells you how much of the mass is made of every chemical. I'll do 2 more examples. What is the percent composition of H2O? So I have 2 different atoms, hydrogen and oxygen. For each of them, I'll take the mass of that part divided by the mass of the whole thing. So the mass of that part divided by the whole thing, and then multiply it by 100 to make it a percent. So in this case, sorry that I changed the layout, H's percent composition is 2 times hydrogen's mass divided by the whole molar mass of H2O. That's the ratio of hydrogen's mass to the whole mass. Then I would do similar thing with oxygen. I would take 1 oxygen's mass divided by the whole thing. And so I will look at the periodic table. Oxygen is about 16, hydrogen is about 1, so I'll plug those numbers in. Hydrogen percent composition, you can just put this into a calculator. It'll tell you that it is 0.11, and oxygen's percent composition, it'll tell you is 0.89. These two should add up to 100, because you should have 100%. Oh, but I forgot one thing. So I like percents like this, like ratios, but to make it a percent composition, technically you need to take these decimals and turn them into percentages by multiplying by 100. So hydrogen's percent composition is 11%, and oxygen's percent composition is 89%. And this makes sense because together they add up to 100%, which is what you want. So 11% hydrogen and 89% oxygen. That's the percent composition of H2O. One more example. What is the percent composition of CaCl3? So you have 2 different chemicals. You have calcium, and you can figure out calcium's percent composition by taking the mass of the calcium atom divided by the whole thing. And you could also figure out chlorine's percent composition by taking the mass of the 3 chlorines divided by the whole thing times 100. So we'll do both of these. The calcium percent composition is 1 of calcium's mass, because that's the part of the mass that's made of calcium, divided by the whole mass, all of it, including the calcium and the chlorines. For chlorine, I would do the same thing, but I wouldn't divide calcium by the whole thing. I would divide these 3 chlorines by the whole thing. So I have to look these up on the periodic table. So I'll look them up. Calcium's mass is about 40. Chlorine's mass is about 35. So you plug this in. You put this into a calculator and you simplify. You will get decimals, but that's because you haven't turned them into percentages yet. These right now are just ratios. You want them to be a percent, so you multiply by 100. And you get that calcium chloride is made of 27% calcium and 73% chlorine by mass. And this makes sense because if you add both these up, you will get 100%. So 27% calcium, 73% chlorine. The last thing is about empirical versus molecular formulas. And this kind of builds on this too a little bit. It's much easier though. So when we're writing down a molecule, one way to do it, which is what we've been doing it, the normal way of writing down a molecule, is by writing down every single atom involved. It's called the molecular formula. So the molecular formula of a chemical might be like C3H6O3. That would be a molecular formula if this atom had 3 carbons, 6 hydrogens, and 3 oxygens. Now there's another way, which is to write down a simplified version. So you can write down the simplified lowest whole number ratio of the elements, called the empirical formula. I haven't taught it to you before. In this case, really you have 3 carbons, 6 hydrogens, 3 oxygens, but notice all these numbers are divisible by 3. So you can imagine a simplified version of this, where you take CH2O. Because if you take all these numbers and you divide them by 3, so you take 3 divided by 3, 6 divided by 3, 3 divided by 3, that would simplify to be 1. This would be 2, and that would be 1. So this thing that we're learning, the empirical formula, it's actually the simplified lowest numbers that you could be using. So let's say you have a chemical, like C6H12O6. And you notice that all the subscripts have a common divisor. In this case, these are all divisible by 6. You can simplify the molecular formula by dividing them all by 6. So originally it was C6H12O6, but these are all divisible by 6, so we can simplify. And you will get C1H2O1. And we don't write the ones. This is called an empirical formula. Why would we ever do this? So we have a mystery chemical we want to identify. In the real world, scientists will often do tests to figure out the percent composition. So we can figure out the percent composition of a chemical, and we can determine that maybe it's 40% carbon, 7% hydrogen, 53% oxygen. So we have a mystery chemical with this percent composition because we did tests and we figured it out. Now this tells us we could just use the molar masses and figure out that if we have this percent composition, the chemical must be some multiple of the empirical formula, like this, CH2O. Now we don't know exactly how many carbons, hydrogens, and oxygens there are, because we know that 40% of it is carbon. Maybe this is like 10 grams, maybe this is like 200 grams or something. We don't know exactly how much in absolute terms the carbon is, but we know that 40% of the whole thing's mass is made of carbon. So we get the ratios, we can figure out the empirical formula, and then we can do other tests to figure out the real molecular formula, by weighing it maybe. So in the real world, in the real actual world, what we would do is we would figure out the percent composition, use that to figure out what the simplified formula is, and then we would do other tests to figure out if they were multiplied to become a bigger molecule, like that, to get the molecular formula. But in this class, we are not ever going to go and do this because it's complicated. We're going to go from the molecular formula to the empirical formula because the state of Texas says that you need to know how to do this. That's why we're doing it. It's not because it's useful. What's useful is going this way, but that's way harder, and you don't have to know how to do that. So in the real world, we use the percent composition to figure this out, and then do other tests to figure that out. But in this class, you're going to go from molecular to empirical just to understand conceptually that there's a difference between them. So, what is the empirical version of this formula? Well, you see H2O, there's sort of a 1 here. There's no common divisors, so it's just H2O. It can be its own empirical formula if there's no simplified version. What about this? I have a molecular formula, C2H4O2. What's the empirical formula? Well, you can look at all these and say, oh, you can divide all these by 2, right? They simplify. These have 2 as a common divisor. So you can divide them all by 2. And what this will turn into is CH2O. CH3O. Well, this doesn't look like anything can divide. I'm going to have a 1 here, a 3 here, and a 1 here. They don't have any common divisors. So this is actually its own empirical formula. I don't have to change it. C6H3O6. Well, all these are divisible by 3. So you can divide them by 3. And then what you'll get is the simplified version. So 6 divided by 3 is 2. 3 divided by 3 is 1. 6 divided by 3 is 2. So this turns into C2HO2. Here are some formulas as examples. The notes are that the molecular formula and the empirical formula can be identical, like in this case they're exactly the same, and in this case they're exactly the same. That's fine if it's already simplified. But if it's not already simplified, then you might have to divide by something to go from molecular to empirical. So that was it. That was everything you need to know for the next test. I hope this was helpful.